Good morning everyone and welcome to today's worked exam answer video. Today you're getting two answers for the price of one because I've chosen to have a look at these two multiple choice questions as they both cover content from the atomic structure topic of the AQA specification, which if you are in year 12 was probably one of the first topics you did this year. If you're in year 13, probably feels like a lifetime ago. And I've chosen these two specific questions because the content is either very commonly kind of asked in this way, which is the case for the top question, or the content is perhaps not so well understood, as is the case in the bottom question. So I thought I'd pair them together in this video. Two for the price of one. Happy days. So the top question is asking us about successive ionization energies for element X. So first thing I guess we need to make sure that we're happy with is what we mean by ionization energy, which is the energy that it takes to remove one electron from an atom. So I guess the formal definition, removing 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of unipositive ions initially. That would be your first ionization energy definition. Then we can do a second ionization energy, taking a second electron off, then a third, a fourth, a fifth, and so on and so forth. That's when we get in the realms of our successive ionization energies. And here they have plotted for us the first 8 ionization energies, and we've got the actual amount of energy needed on the y-axis here. And what we can see is the amount of energy needed to remove the first one, not that large, but still energy will be needed to take that electron away because it's going to be held by the protons in the nucleus. When it comes to removing the second one, we need slightly more energy, and we need more energy for every single electron we remove. And that is based on the fact that if we're removing an electron, the proton number stays the same, and therefore the same number of protons are then attracting fewer electrons. So let's say that we started with 5 electrons and 5 protons in our atom. If we take 1 electron away in the first ionization energy, we would still have 5 protons, but now they're only attracting 4 electrons. So those 4 electrons will be held more tightly. Then once we've managed to get away another one, we would then have 3 electrons left, but we still have 5 protons. So again, the 5 protons are going to hold those 3 even more tightly. Get another one off, then we've only got 2 electrons, 5 protons, you get the idea. So it's always going to take more energy the more electrons we continue to remove. However, you might have noticed this big, it's not that massive, I don't suppose, but this jump from when we remove the third electron to where we remove the 4th electron. So up until that point, the jumps in energy required were small-ish, fairly uniform, and after we've removed the 4th electron, again, the increase in the amount of energy needed to remove the subsequent ones, fairly uniform. So what on earth is going on here? This comes back to thinking about the factors that affect ionization energies, and I've already spoke about one of them, which is the charge on the nucleus. Another really important one here is distance of the electron from the nucleus, and with that comes shielding, because if we've got an increased distance away from the nucleus, there will, alongside that, be an increasing shielding because you'll have more inner electron shells. And it's distance that's really important here. So what this is showing us is that the first 3 electrons, all being taken from the same main energy level, when it comes to removing the 4th electron, it takes substantially more energy to remove the 4th electron. Therefore, the 4th and 5th, 6th, 7th, 8th are all being removed from a main energy level that is closer to the nucleus. So bearing that in mind, what we can then say is that these 3 electrons here they will be the number of electrons in the outer shell. And when we're thinking about taking these electrons away, we will always take from the outer shell and work towards the nucleus, okay? So those are our outer shell electrons, and then when we take the fourth electron away, we have removed this one from a main energy level closer to the nucleus. So the distance between the protons and the electron that they're holding on to that we're trying to take has decreased. So the attraction between the protons and the electrons will be stronger if the distance has decreased. Now, obviously this is a multiple choice question, so I didn't need to annotate anything like that on this question. However, this question has come up as a 3-marker before as well, where you've got to identify the element and then you've got to explain how you knew that it was that particular element in that period. So that would be essentially what I've done there. I'd say it's element this because there are this many electrons in the outer shell, and when it comes to removing this one, the big jump in energy shows that it's being removed from a main energy level that's closer to the nucleus. So that would be my explanation for a longer question. Here, in terms of working out what the element is, we need to figure out which of these options has 3 electrons in its outer shell. So not nitrogen, because nitrogen has 5 electrons in its outer shell, not phosphorus, because that also has 5 electrons in its outer shell. Aluminium and boron would both have 3 electrons in their outer shell because these are both in group 3. Now, it hasn't told us which period this element is in. Sometimes it will, and if it said it was in period 2, it would be boron, and if it said it was in period 3, it would be aluminium. But we're not told that here, so there has to be something else that we can make use of on the graph that will tell us which of these 2 group 3 elements it is. And the clue is the fact that they have plotted 8 ionization energies. And if we look at the atomic number of boron on the periodic table, it's 5. And the atomic number of aluminium is 13. We cannot take 8 electrons from boron if it's only got 5. Therefore, this is representing the successive ionization energies of aluminium because we've got the 3 in the outer shell, and because we can then continue to remove all the way up to 13 if we wanted to, but we can certainly make it to 8. So it's not boron based on the number of electrons that it has, so therefore it has to be aluminium. That has been done a couple of times on questions like this as well, whereby they've chosen 2 elements in the same group and you've had to use the graph and the number of ionization energies to decide between 2 elements in the same group in different periods. The other way that they might present this information is in a table, or they might just list the 1st, 2nd, 3rd, 4th, 5th, 6th ionization energy. You can still be looking for the big jump in amount of energy needed, just like we've done here. In a table or a list, it's just a little bit less visual, but you would be using the exact same skill set if that's how they presented the data. Okay, so that's the first question. And then the second question is thinking about chlorine isotopes and how we would observe the peaks in a mass spectrum of diatomic chlorine gas. So there's a few key pieces of information in here. Number 1, we're told that we've got 2 different isotopes, 35, 37, and that those are found in the ratio of 3 to 1. So 75% of all chlorine atoms will have a mass number of 35, 25% will have a mass number of 37. We're then thinking about Cl2. So the first thing that I might suggest we do here is we think about what combinations we can have of those 2 isotopes in a chlorine molecule. So in terms of analysing this in a mass spectrometer, we would have our chlorine molecule, which would need to overall be ionised so that it could then be accelerated and detected at the other end. But what combination of these chlorine isotopes might we find inside our molecule? Well, we might have this first one being chlorine 35 and the second one also being chlorine 35. We might have this first one being chlorine 37 and the second one also being 37. Or we might have one of each. And those would be our three different combinations for the types of atom that could make up that molecule. Now, when it came to that whole molecule hitting the detector, we would then get the MZ values from those mass numbers. So if we had 2 chlorine 35 atoms in our molecule, the mass to charge ratio would come out as 70. So we'd get a peak at 70. If one was 35 and one was 37, we'd see a peak at MZ 72. And if they were both 37, we'd see a peak at MZ 74. Now the M and Z is mass over charge, the mass 35 and 35 to get 70, Z is the charge, and we assume that all of the molecules, when they undergo ionisation, will be, when electron impact occurs, will only lose one of their electrons, so we'll only be making unipositive ions. There may be a very small amount that end up being 2+, but they would be very minor peaks on the spectrum, and these are the ones that we need to focus on. So we can already tell that there's going to be 3 peaks. So if I have a look at the answers, we've got A that says there's only going to be 2 peaks. We've got D that only says there's going to be 2 peaks. So they are both wrong because we have not got the right number of peaks. The middle two have got the right number of peaks. They've got the right MZ values. The difference is in this ratio here. So it's either 9:6:1 or 9:3:1. Now, going back to that first sentence, we know that the chlorine isotopes are not equally abundant as each other. Therefore, we're not going to have all of these possibilities being equally likely. There are way more chlorine 35 atoms in a sample of 100 than there are chlorine 37 atoms. So to try and get 2 chlorine 37 atoms in the same molecule, it does happen, but it's nowhere near as likely as having 2 35s. So what we need to do is obviously put some numbers to that, be a bit more quantitative than just saying this is very likely, this is very unlikely. And the way that we would do that is to consider this ratio, and I'm going to draw a probability tree so that we can see in terms of fractions what the chances are of the first chlorine atom in the molecule being 35 or 37, then what's the chances of the second one being 35 or 37, and then we can go through the probability tree and figure out all of the probabilities. Now you might be thinking, oh my goodness me, this is a lot of work for a 1-mark question, and you would be correct. So whilst it's really important that you're able to deduce what I'm about to draw, because some longer questions have come up in the past which have basically asked you to explain where this ratio comes from. However, for this multiple choice question, you'd kind of want to know that ratio off by heart, because then you could go, well, I know there's going to be 3 peaks because there's 3 possibilities, and actually the ratio is this. If you had to sit and draw this probability tree, that's probably going to take you longer than you can afford for this question. However, if you know how to do the probability tree and you know that it'll get you the right answer, then only you can know whether it's worth spending that extra time to get the mark, potentially not get a mark elsewhere. That's the beauty of multiple choice questions, everyone. So on my probability tree, we've got the first chlorine atom. Now that might be chlorine 35 or it might be chlorine 37. Then after we've sorted the first chlorine atom out, we then need to think about what the second one in the molecule is going to be. And again, the second one can be 35 or 37. So now I'm going to add the probabilities on. So if the ratio is 3 to 1, it's going to be 3/4 to 1/4. So there is a 3/4 chance that the first chlorine atom will have a mass number of 35 and a 1/4 chance that the first atom will have a mass number of 37. Those probabilities don't change for the second chlorine atom. It doesn't suddenly become more or less likely that the second one will be a 35 or a 37 based on what we've got for the first one. So those fractions would be the same for those strands of my tree as well. Now, if I want to figure out what the likelihood is of it being a 35 and a 35 together, I would need to times through the tree. So we're going to do 3/4 times 3/4, which is going to give me 9/16. And that 9/16 is going to be for my MZ value of 70, because 35 and 35 is 70. So that's where the 70 and the 9 come from in both of these options. If we look at 37 and 37 together, we've got 1/4 times by 1/4, which is 1/16. That is far less likely to happen than we are to get 235 chlorine atoms in the molecule. And that would be for the MZ peak of 74, because we've got 2 chlorine 37s, and that's where in both of these options the one at the end comes from. Now, in the middle we have the same ultimate outcome, but it's achievable in two, they're not slightly different ways from a chemistry point of view, but from a probability point of view they actually cast as separate scenarios. So if the first chlorine atom was a 35 and the second was a 37, we'd have 3/4 times 1/4, which is 3/16. And if one is 35 and one is 37, that's going to give us a mass to charge ratio of 72. But if we then go with 37 as being the first chlorine atom, 35 as the second, then that will also give us 3/16 for the likelihood that that will happen. And here the MZ value is still going to be 72. And the fact that the chlorine atoms have switched round actually means nothing at all. So what we then do with these numbers is, because the outcome is the same, is we would then add the 3/16 and the 3/16 to get 6/16. And that is why the correct answer here is the second option with the 961, not the 931, because the two ways that we can make the mass number of 72, 3/16 and 3/16, is 6/16. And 9 and 6 and 1 make 16/16. So yeah, definitely easier to remember that ratio for questions like this. Definitely need to be able to, however, draw that out and be able to show that that's why the height of the peaks is in that particular ratio for our chlorine molecule. Now, chlorine's the example they use more often than anything, I might have seen them use bromine once or twice, and that's it. And the reason why they use chlorine is because they're not equally abundant isotopes. They're in that ratio of 3 to 1. The bromine isotopes are essentially 50-50, so you don't get the same difficulty when it comes to figuring out the probability of these different mass to charge values from existing. So it will be chlorine that they ask this about, but I guess just be prepared to apply the same logic to other examples, whereby if they give you the ratio of abundances, you can put those in as fractions in exactly the same way. Hopefully that's been helpful, guys. Any questions about either of these multiple choice questions, as always, please drop me a comment on the video, or you can send me an email to missgtutoringandresources@outlook.com. Thanks so much for watching, guys.